My talk will be about KATRIN, and it's great to see so many attendants interested in this experiment. And I called this seminar talk "The Challenge of Determining the Absolute Neutrino Mass," because I will hopefully point out a few challenges, some of that we have overcome and some that we are still facing and improving. And so without further ado, I just start with an outline. And yeah, so in my talk, I will start off with a little bit of motivation, so direct neutrino mass measurements and neutrinos from beta-decay in the way we measure them at KATRIN, and then give you an overview of the KATRIN beamline. And then I will go on a little bit of a detour into some of the major systematics that we are investigating and that are becoming more relevant as we are taking more data. And then towards the end of my talk, I will quickly outline our recent results, which have been published in 2019. So that's our latest result. Of course, there's more to come. And at the end of the talk, I will just give a brief outlook into the next step and future perspectives. And as you can see in this picture, the KATRIN inauguration was in 2018. So it has been about 2 years until now. And so, of course, since then, we made some progress and also took our first data. And hopefully in my talk, I can explain and outline a little bit of this progress. And the goal of KATRIN is to measure the neutrino mass. The best upper limits before KATRIN were about 2 eV, and the goal is to push it down by 1 order of magnitude. And therefore informing the standard model of physics. And to give some background of neutrino theory, let's start with the standard model of particle physics. And we know that neutrinos in the standard model have a mass of 0, but of course from oscillation experiments we know that the mass is not 0, and therefore we have the PMNS neutrino mixing matrix, where we have 3 mass eigenstates and 3 flavor eigenstates, and the mixing matrix describes these states. And from neutrino oscillation experiments, we know the mass differences, and this is shown here. Because we only know the mass differences and we have 3 states, we can have normal and inverted ordering. Inverted ordering, the mass differences and the mass states are inverted. And the problem is that we know the mass differences, but not the absolute mass scale. And so we cannot distinguish right now between these 2 orderings, and also we don't know the absolute scale. So on this axis, there are no values because the mass of the lattice eigenstate is unknown. And on top of that, we also have some hints, at least for stereo neutrinos, which would extend this model again by at least 1 more flavor eigenstate, mass eigenstate. And so we can say that the absolute neutrino mass scale is one of the big open questions for the reasons I just mentioned. And we know that neutrinos are massive particles, but we only know mass limits. And so to determine the neutrino mass, there have been 3 different approaches established, and I try to outline them here a little bit. One approach is from cosmology, where we measure the sum of the mass eigenstates, which corresponds to this equation. And this is done by both satellite measurements and ground-based telescopes investigating the sky and especially the CMB. In addition to that, we also have neutrinos double beta-decay, which is then on this side, Gedda, Legend, Fiore, Cupid, and so on, where we measure the coherent sum of the neutrino mass eigenstates. So this is a little bit different. And then, of course, we have the approach that KATRIN is following, which is the kinematic approach, where we measure the incoherent sum of neutrino mass eigenstates. And so, although all these different approaches measure slightly different observables, they can all inform the standard model of particle physics and give us access to the neutrino mass scale, of course, with some requirements that depend on the different approaches. And I want to go a little bit more into the cosmological part before I come back to KATRIN, because cosmology currently provides the best upper limits of the neutrino mass, even down to 0.1 or even slightly below eV, depending on which data you analyze. And currently, this is a combination of different experiments and also a combination of different observables. And depending on the observables that are combined, you can reach pretty good upper limits and even approach the limit where we could rule out inverted ordering, which is about 0.1 eV. So we are already approaching this. But we should also not forget that the interpretation is based on the standard model of cosmology, and extended scenarios would weaken the bounds on the neutrino mass. And this is not a competition, because the direct mass measurements are complementary to the cosmological investigations, and the neutrino mass is one of the few cosmological parameters that can also be tested in lab experiments. So by measuring the neutrino mass, in addition to these cosmological results, we could inform the standard model of particle physics and the cosmological model by testing the results gained from cosmology in a lab experiment, and also the other way around. And yeah, so these two approaches, and also, of course, the neutrino stable β-decay, are really just three sides of yeah, the same question. And yeah, the point of this is to highlight that lab experiments are still complementary. And so for the KATRIN experiment, so now let's have a closer look at the KATRIN experiment on the next few slides. In the KATRIN experiment, we measure the neutrino mass from tritium beta spectrum, and the observable in this case is the squared neutrino mass of the electron neutrino. And what we do in KATRIN is we observe tritium beta decay, which is shown here. So tritium decays into helium, emits an electron and an electron antineutrino. We ignore the electron antineutrino, but we can measure the energy of the electron. And by doing so, we can determine the differential energy spectrum of the tritium beta decay, which is shown here. It goes up to an energy of about 18.6 kilo electron volts because of the endpoint of tritium, and the half-life of tritium is about 12 years, which gives us a good trade-off of an accessible energy range and also a high source activity. In KATRIN, we measure this spectrum kinematically by measuring precisely the electron energy in this endpoint region, which is shown here. And in the endpoint region, we can distinguish the spectral shape of the spectrum, and we see an influence of the neutrino mass. So in this case, it's 1 eV mass, where you can see a clear distortion in the spectrum that we can resolve by our measurements. At KATRIN, we measure the integrated spectrum, not the differential spectrum. So this is an important thing to keep in mind. So the differential spectrum shown on the last slide is converted into an integral spectrum in our measurements. And what we do to determine the spectral shape is we perform an energy scan in the endpoint region. So in this figure, the endpoint is close to the 0 value on the energy axis, and we vary the retarding energy by a few eV around the endpoint. And the retarding energy is just a filter energy, which means electrons above a certain energy threshold will be transmitted, and therefore we effectively perform an integration of this differential spectrum to determine the spectral shape. And then we can apply a fit with a few parameters, including the endpoint and the neutrino mass, to the spectrum. And you can see here that the influence of the neutrino mass is most prominent in a few eV range below the endpoint. So in this case, it's 5 eV. It depends on a few factors, of course. But for this reason, we perform the measurement in a few eV range around the endpoint. And then we have a measurement time distribution, which means how much time we spend on each retarding potential. And you can see here, it's very much peaked close to this region where we are most sensitive. And of course, we can also use this measurement time distribution to optimize our sensitivity. For example, if you have higher background, this would shift a little bit to the left because some of the spectrum is not accessible. And so by using the measurement time distribution, we can optimize our sensitivity depending on our experimental parameters. Now, the measurement of tritium beta decay is a challenge because only a fraction of tritium decays is in the endpoint region. And this is shown here. Again, in the spectrum, if you look close to the endpoint, you see that the majority of decays is actually at much lower energies, and only about 10 to the minus 13 of all decays is in the last EV. And then if we want to measure in that region, we have to take a few steps to get there. And one is to have a very strong beta source, which has, in our case, 10 to the 11 decays per second at full source activity. We need a low background of 0.1 counts per second, and an excellent energy resolution to be able to determine the shape of the spectrum in this narrow region around the endpoint. So we need an energy resolution of about 1 eV and a precise understanding of the spectrum that goes into our fit. And the final sensitivity goal of KATRIN is open to EV after 5 years of measurement time, which is equivalent to 3 years of data. And we are slowly getting there. We have now a few runs, but I will come back to that later and first give you a quick overview of the KATRIN beamline. So we start here on the left side with the source and transport section. The source is here. And in the source, we have tritium β-decay with 10 to the 11 decays per second. We have a windowless gaseous tritium source, which means in principle, tritium gas and decay products can leave the source and go further down the beamline. To prevent that, we have a transport section, which is a combination of two components which achieve a tritium retention of 10 to the 14 or better and reduce the amount of tritium ions, for example, reaching the spectrometer and detector section. And the spectrometer and detector section is here on the right side. We have a pre-spectrometer, which filters out the low energy part of the spectrum, which we are not interested in. And then we have the main spectrometer, which performs the energy analysis to achieve or to measure this integrated spectrum of the β-decay. And you can think of this as kind of like a roller coaster where the electrons from the source are emitted with various energies near the endpoint, and then they have to overcome a potential wall that is established here in the spectrometer, and electrons which are fast enough, so if they have enough energy, they can make it through to the detector, and electrons which have not enough energy are reflected back to the source, and then by varying the energy we can measure the spectrum. And so the detector in our experiment is just an electron counter, because the actual analysis we do with this main spectrometer. Now let's quickly go over a few components. The windowless gaseous tritium source, as I already explained, is a windowless source which has a closed tritium cycle where tritium is continuously injected in the center and then pumped out at the end. And in this tritium loop, the tritium is also purified so that we can achieve a stable tritium purity of better than 95% and also a good stability of both temperature and source activity on the 0.1% level. The tritium in the source is, as I said, mostly tritium with more than 95%. There's also some so-called isotopologues, which are combinations of molecular of tritium atoms with hydrogen and deuterium. The source activity is up to 100 gigabecquerel at our nominal column density of 10 to the 17 per square centimeters. And this requires a large amount of tritium throughput because this purification. And this is done in the tritium lab in Karlsruhe at the KIT. And so they provide the infrastructure for this complicated tritium loop system. Then the next step in the setup is the differential and cryogenic pumping section or transport section, as I explained it earlier. We want to reduce the tritium flow from the WGTS by a few orders of magnitude. And for this, we have two sections which have both a tilted beamline, and we also combine this with ion blocking electrodes. And the first step is a differential pumping section where the electrons go around the tilt in the beamline, and the heavier ions and so on don't follow because of their mass. So they are pumped out by TMPs located in the differential pumping section. And after that, we have a cryogenic pumping section where we have argon frost on a gold layer on a cooled beam tube surface, and this has a high sticking efficiency for tritium molecules, so they stick there and then decay eventually or get pumped out in the end and can't reach the spectrometer. And this is very efficient, so we achieved flow reduction by more than this requirement. We achieved like 10 to the 16 instead of this 10 to the 12, and this is well within the requirements, and also it's one way of reducing the background in our spectrometer from tritium. Now in the spectrometer and detector section, we perform the energy analysis of the signal electrons, as I already mentioned. We have a magnetic guiding field where the magnetic field goes from a few Teslas at the entrance and end of the spectrometer to less than a millitesla in the center, and I will explain on the next few slides why we use the setup. The spectrometer is called McE filter, and it acts as a high-pass filter for the signal electrons with a retarding potential that is close to the endpoint, so typically 18.6 kilovolts negative. We achieve an energy resolution of 1 to 3 electron volts at this endpoint, and also a large acceptance angle. I will come back to the acceptance angle on the next slide. The retarding potential is provided by a precision high voltage regulation system, which can reproduce and stabilize voltage on a 20 millivolt level, which is quite an achievement at this kilovolt of energy that we're measuring at. And our detector at the end is a 148 pixel silicon pin diode with additional post accelerations to improve the signal to noise ratio. And the pixelated detector can also be used to resolve radial and azimuthal dependencies in our beamline. Before I explain the McE filter, I want to go back a step to explain the electron spectroscopy that we perform at KATRIN. And if you come back to the integral spectrum, like it's shown here, we have the rate against the retarding energy. And the integral spectrum measurement means that if we set a filter energy or retarding energy of this value, for example, then all the electrons that have a higher energy will be transmitted and counted. And then we change the retarding energy to some different value, and then we only count the electrons that go lying in this energy range. And therefore, we can perform this measurement. And now in the ideal case, if you go on the right side, this is a response function. In the ideal case, it means electrons that have an energy below the retarding energy will not be transmitted, and all electrons that have a retarding energy above this threshold will be transmitted. So you would end up with this orange curve in this figure. But due to the design of the McE filter, there's some energy dependency. And so this means to transmit all electrons in our current setup, the electrons need to have 2.8 eV more. So in this range between 0 and 2.8 eV, the transmission probability is less than 1, and it increases with increasing energy. And so to interpret this response function, the important thing is that the 0 is essentially the retarding energy, and a higher energy means the electrons have more energy when they are entering the spectrometer than they need to at the endpoint. And so I want to explain now more why this where these 2.8 eV of energy resolution come from. And so in the McE filter, we have not only the energy filter, but we also have magnetic adiabatic collimation, which is the other part of the McE name. And the problem is, or yeah, let's call it a problem for now. The problem is that our source is isotropic, which means a few electrons would be emitted with their momentum pointing along the magnetic field line, which means that all the kinetic energy is available in the longitudinal component relative to the magnetic field line. So this would be if the momentum would be equal to this longitudinal vector. And that means that the full kinetic energy of the electrons would be available in the center of the spectrometer and the analyzing plane where we apply the retarding potential. But since our source is isotropic, there are also electrons emitted which have an angle relative to the magnetic field line, like it's shown here. And this means that less energy is available in the forward direction on the beamline, and so this energy is not available to overcome the retarding potential. And of course, with our isotropic source, most of the electrons would have angles pointing away from the field line. And so the McE filter achieves a collimation by using the fact that the magnetic moment in adiabatic propagation is constant. So the ratio of transversal energy and magnetic field is constant. And we combine this with a decrease in the magnetic field strength, as I already said, of about a factor of 1 to 20,000. And this effectively achieves a momentum transfer from the transversal momentum to longitudinal momentum. And this means that at the analyzing plane, where we have the retarding potential, almost all of the kinetic energy of the decay is available to overcome the retarding potential, even if the electron was emitted with an angle to the field line. And of course, this is not perfect because the magnetic field ratio can't be infinite or 0. And so this is the reason why we have this energy resolution, which is typically on the order of 1 eV, because this is determined by the magnetic field ratio. And so this means that electrons with a higher angle need a little bit extra energy to overcome the potential wall in the spectrometer. And so these are the most important things to know about the McE filter. I will come back a little bit to the McE filter later on. But of course, the spectrometer and the McE filter is only one part of the setup. I will also want to explain a few more things. And one of the important set of devices are monitoring devices. And to highlight a few of these, we have a laser Raman system in the source, which is located here. The laser Raman system can actively monitor the tritium purity and the gas composition. So it can also keep track of the isotopologues that I introduced earlier. And you need this to monitor the tritium purity and the source stability online during the measurement. And this is done actively while the gas is circulating in this tritium loop. In addition to that, we also have ways of measuring the source activity directly by measuring the decay rate, and we use a combination of beta-induced X-ray spectroscopy at the source and a so-called forward beam monitor, which is located here just before the spectrometer section, which can be injected and removed from the beamline to perform dedicated calibration measurements. We also have a precision high voltage system where the retarding potential that we apply to the spectrometer is monitored at the ppm level, and for this we have a combination of a readout chain that uses a custom-made high voltage divider and a separate spectrometer, which is a smaller version of the McE filter, which measures krypton 83 lines that have a very, very small natural line width. And these two spectrometers share the same potential, so we can use this krypton line measurement to perform an absolute calibration of our retarding potential that we apply to our main spectrometer. In addition to that, we also have calibration electron sources. One source is located behind the source. It's a so-called rear section, and this is a high-intensity electron gun, which is an electron source that provides monoenergetic and angular selective electrons. Angular selective means we can determine the angle of the electrons relative to the field line to, for example, measure the McE filter characteristics that I explained before. The electrons are generated via photoelectric effect from UV light. We have a pulsed UV laser that can also be used for time-of-flight measurements, where we can investigate the time it takes an electron from the laser pulse until it ends up at the detector. And we achieve a typical line width of 0.15 eV and an angular range from 0 to the maximum angle. And we can use this E-gun to perform measurements of the spectrometer transmission properties, to monitor the column density, and to perform energy loss measurements. In addition to that, we also have krypton sources in the main beamline. So this is not the monitor spectrometer that I explained before, but krypton sources in the main beamline. And we can use gaseous krypton in our source, where we just fill the source with krypton gas and increase the temperature to make sure that it doesn't freeze out. And this can also be combined with tritium in different ratios. Excuse me. In addition to that, we also have a condensed krypton source, which is located behind the transport section. So again, here at this part. And in this case, we have krypton 83M condensed on a cold surface. And this is a smaller beam spot that is movable around the flux tube. So the gaseous krypton source illuminates the whole detector. The condensed krypton source has a smaller beam spot that can be moved around. And we use krypton because one of the krypton lines, the K32 line, has an energy of 70.8 keV, which is fairly close to the tritium endpoint. So this is a nice way of doing calibrations in the same energy range. And in addition, krypton also has energy lines at lower and higher energy, which we can use to study the energy linearity and also just perform measurements at different energies. So this is why krypton is one of our preferred sources for doing calibration measurements. And we use this to study source plasma effects and also to investigate the transmission and the response function of the spectrometer and the entire experiment. Now, before I go into some of the systematics, I also want to highlight the simulation software that we are using to investigate and study our experiment and to optimize our design. This is the Cassiopeia simulation software, which was developed in the recent years at the KATRIN collaboration and is now also used by other experiments, for example, Project 8. And this software framework allows flexible geometry definition and configuration. we have electromagnetic field solver, which is called ChemField, and then the particle tracking part, which is Cassiopeia. And the public version is available on GitHub if you're interested. And we can use this to do precision calculation of electron trajectories, for example, for stored particles in our spectrometer, which is shown here in this picture. And we can also handle complex simulation geometries. So in this picture, you see on the left an actual picture of the inside of the main spectrometer, and on the right, a 3D model based on technical drawings that introduces the main spectrometer into our simulation. And you can see that this is very much in agreement. And so this is the level of detail that we can handle with the ChemField software and do particle tracking with Cassiopeia. Okay, now let's have a look at the recent progress that we made in KATRIN. So this picture is probably in one way or the other known to many of you. It's from almost 2 decades ago. And so in the meantime, we made a little bit of progress. And let's go back to spring 2017, where we had the first transmission of electrons through the beamline, which was then followed about a year later after some more systematic studies by the so-called first tritium campaign, where we injected a very small amount of tritium for the first time into our source and performed measurements. We then had more systematic studies. Then in spring 2019, we had the first neutrino-mass run, where we had actual sensitivity to the neutrino mass, and this is also our first published result from last year. And then in fall 2019 and spring 2020, we had more neutrino mass runs that are being analyzed. And so for now, I want to focus on the first neutrino mass run where we published our recent results. And to put this a little bit into context, we have different data taking periods, which we call KNM 1, 2, 3, and so on. So this means KATRIN neutrino mass. KNM 1 is the first neutrino mass run that I just mentioned. In this run, we had a measurement time of 22 days and a source activity of 2.5 times 10 to the 10, which is lower than the nominal source activity for reasons I will explain later. So this was at a reduced source activity. And this luminosity plot, so to say, shows you the number of β-decays in total and for tritium mode and for neutrino mass scans over time. And you can see that it increases. Then in the second neutrino mass run, we had a measurement time of 31 days and a much higher source activity. So you can see the source, luminosity increases much steeper because of the higher activity. And then the third neutrino mass run was done in this summer, just a few months or weeks ago. And here we had a measurement time of 27 days, and the analysis is still ongoing for this run. And then the fourth neutrino mass run has started just earlier this month, or at the end of last month. And so we are now in the fourth neutrino mass data taking period. And the beamline configuration for the first neutrino mass run is shown on this picture. We have our source at reduced source activity, as I already mentioned, magnetic field of 2.5 Tesla in the source. Then at the spectrometer, we have magnetic field, maximum magnetic field on the beamline, which is at the end of the spectrometer of 4.2 Tesla. The minimal magnetic field at the analyzing plane of the spectrometer is 0.63 millitesla, and this gives us an energy resolution of 2.8 eV. And then at the detector, we were able to use 117 of the 148 pixels that we have because the rest of the pixels were shadowed by parts of the setup, or the pixels showed too high rates. So this is a little bit limiting our sensitivity, but we can compensate to that to some amount by changing the mapping of the source to the detector. And of course, this is also things we are improving on. So for the next measurement phases, we improved many of these factors. And with this setup, if you have a look at our systematics, the systematics are shown here. This is a table that is part of our published result in PRL. And you can see there's different systematic contributions that we consider. So source properties, magnetic fields in the beamline, final states, fluctuations of the between the different scans and backgrounds. And if you add up all of these, the total systematic uncertainty is 0.32 EV squared, while the statistical uncertainty is 0.97 EV squared. So we are in this run totally dominated by statistical uncertainty. But that does not mean that we should ignore systematics. And if you look at this table, you also see that the most dominant contribution from systematics is the non-Poisson background, and I will explain on the next few slides. what this is about, and then also cover a little bit of the other systematics that are shown here, which have all a relatively small contribution in comparison, but we hope that the background level can be decreased, and then these systematic contributions will become more important. And so this is also something that we are continuously improving on. So the background sources at the main spectrometer are summarized on the slide. So this is a picture of the main spectrometer with a few possible background sources that have been investigated and mitigated. For example, panning discharges due to the electron setup in the spectrometer have been investigated and found to be no issue. We have done measurements with external radioactive sources and found no issue from, no contribution from this either. The same goes for cosmic muons, which would also be able to increase the background level by performing interactions with the stainless steel wall of the spectrometer, and then electrons would be emitted on the inside and entering our setup. This is also has been investigated and tested and does not contribute to our background. And besides some intrinsic background from the detector, which is also being improved, we have a remainder of two major background sources in the spectrometer. And one are radon decays, which are triggered by emission of radon-219 from our getter pumps. So we have getter pumps at the spectrometer to achieve ultra-high vacuum, but the getter pumps also emit radon. And the problem with radon-219 is that it can reach our spectrometer, then decay in the internal volume, and then the trapped electrons can generate more electrons that then are transmitted to the detector and share the energy region with the signal electrons from tritium. So this is background that can't be distinguished by the energy alone. And so what we did to mitigate this effect is we have liquid nitrogen-cooled baffles, which block the line of sight between the getter pump and the spectrometer volume, and this reduces the contribution by radon by 95% or so. So this is very effective. But after fixing all these issues, we were surprised to find that there's another component, which is the so-called Rydberg background, and which is now the dominant part. So the yellow part in this pie chart is the Rydberg background, which is the dominant component of our background systematics. And the Rydberg background, as I mentioned, it was a surprise to us to find it because it was not foreseen that this is a process that can happen in the spectrometer. And so we know that the radon background is suppressed for the reasons I just mentioned. We know that the background from Rydberg comes from, it's distributed in the entire volume of the spectrometer, so it's not very much increased to the outside, but happens in the entire volume. We know that it's not radioactive decays or trapped particles. And so we did more investigations and finally found an answer to explain this higher background, which is the Rydberg background model. And the way this goes is that we have some lead-210 in the stainless steel walls of the spectrometer where Rydberg atoms are created. And then these particles are neutral, so they can enter the spectrometer volume without being blocked by potential or magnetic fields. But because they are Rydberg atoms, they can also easily be ionized by thermal radiation. And so since we operate the spectrometer at room temperature, the thermal radiation is sufficient to ionize these Rydberg atoms. And then electrons are emitted after the ionization. The electrons gain energy from the electric potential and then again share the same energy region with the tritium signal electrons. So this is again background that is hard to suppress on the detector, but we are looking into options to suppress the generation mechanism. And as I mentioned, this is the major contribution of our current background. However, we also did background measurements during the first neutrino-mass run, and we see a very stable rate, as you can see here. And we also find that the background is not exactly Poisson distributed, but there's a slight non-Poisson contribution as well. And the problem with this non-Poisson distribution is that it increases the impact to our systematics. So this is one more reason why we should find ways to suppress this background component. And I already mentioned we have some countermeasures, for example, for the radon background, and we are also working on further improvements to reduce this background more and more as we are taking more data. Now, a few other systematics. I will only go quickly through this to stay in time. for this talk. So a few sources of systematics are highlighted here. For example, gas dynamics in the source, electron scattering in the source, energy losses, ions, contributions from the beta spectrum, electromagnetic fields in the spectrometer. And so these are all things we need to understand well to really perform this fit on the integral spectrum. And in the design report for KATRIN, which is from 2004, 5 major systematics were identified, which is the final state contribution, because we have molecular tritium. The final states play a crucial role. We have the energy loss, which is describing the energy loss of electrons in the source, because electrons can scatter on tritium molecules in the source and then lose energy. Then the source stability or fluctuations of the column density by voltage, and again elastic scattering, which is so this is the scattering itself. This is the energy loss, which describes the actual energy loss of the electrons to scattering. This is why it's split up into 2 fractions. And the total systematic budget is matched to the statistical uncertainty for 3 years of data taking. And this also means that the first science runs are dominated by statistical uncertainty, just as I've shown before. So this is to be expected, but as we gain more data, we also need to understand our systematics better, of course. And then after 36 months, we should reach the target sensitivity goal. And yeah, to go a little bit deeper into systematics, I want to start with the transmission and response function, which I already explained a little bit earlier. So the response function, again, it describes the transmission probability of electrons through our spectrometer and also through the entire beamline. And again, in the ideal case, we have a step function where all electrons above a certain energy are transmitted and all electrons below a certain energy are not transmitted. But due to the McE filter, we have this, this slope, which is describing the energy resolution, and in our case, it's 2.8 eV. But in addition to that, we also have electron scattering in the source, and when electrons scatter inelastically, they also lose energy. And this means that if the electrons lose energy, they also effectively need more energy to be transmitted. So if the electron loses 12 eV of energy, then we need 12 eV surplus energy to compensate this energy loss, and then this is why you see an increase in the transmission probability after this 12 eV line. And then if you go further to high energies, we transmit more and more electrons because we compensate more and more for the energy loss that was lost in the source. And so this is one more example where we need to precisely understand our setup to make sure that the response function which goes into the fit is modeled well. And in addition to that, we also have cyclotron radiation over the 70-meter long flight path between source and detector in the high magnetic field. So electrons also lose energy through cyclotron radiation. But the more important part are electron scattering. And also we have some radial inhomogeneity of the spectrometer field, which is shown here. So this is a pixel map of our detector, and it shows the magnetic field at the inside, at the center of the spectrometer towards the outside. And you can see there's some radial inhomogeneity, which can be investigated and measured by calibration sources. And our pixelated detector allows us to resolve this radial inhomogeneity. And then essentially in the fit, we have different response functions for the different pixels and can treat these effects individually. The source column density affects the source activity, of course, but also the electron scattering. So it's a quite important parameter. And we can do regular calibration measurements with our electron gun to investigate the source column density. This is a figure of the source column density during our first neutrino mass run. You can see the rate is fluctuating at least in the first half or so. And the reason for that is that we had fluctuations due to tritiate methane freezing in the capillary of the tritium loop, which was not foreseen, but it's now solved. And this is the main reason why we were operating this first neutrino mass run at a lower column density, because the amount of freezing depends on the injection pressure and tritium throughput. And so by reducing the amount of tritium that goes into the source, we were able to mitigate these effects and then achieved a much more stable column density at the end of this neutrino mass run. And by now, this is solved by both by thermal cycling of the source and also by the refurbishment of the gas capillary pipelines to avoid this problem. So in future runs, we could achieve a much higher source activity, because this is no longer a problem. With the EGAN, we can also determine the source activity or the column density by shooting EGANs, electrons, through the source. And therefore, electrons that go through the source are exposed to some amount of scattering on tritium molecules. And if we know the energy loss response, then we can use this to determine the source activity or the column density by observing the amount of energy that electrons lose. And this is shown here. We can measure at different surplus energies up to 200 eV above the retarding potential, and then see the rate behavior over this energy range. And then depending on the column density, we see that the behavior or dependency of the rate on the energy changes, and we can use this then to do calibration measurement of the column density. And so the EGAN is a tool which we can use for this by performing regular calibration measurements. Now to get into the electron scattering, the electrons can scatter elastically, which is in effect it's not so important here, but they can also scatter inelastically. And if they scatter inelastically, they lose about 12 eV or more in the scattering process. And so this energy loss function here describes the energy loss through scattering. And this is one thing that we need to include in our model. And in addition to this, it's also convoluted for multiple scatterings, because with a higher source column density, electrons can also scatter multiple times. And then we have a convolution of the spectrum and also scattering probabilities for no scattering, one-time scattering, two-time scattering, and so on. So this convolution enters the response function, and then the response function enters the integral spectrum model. And so we need to understand the energy loss function quite well, and we found that we can actually measure this again with the EGAN, which has not been done in this precision in the predecessor experiments. This is a very new approach to measuring this energy loss function. And we use the EGAN in a combination of an integral mode where we measure the response function, and a differential mode where we measure the time of flight of the electrons. And then a combination of which gives us the energy loss function, where you can see here a shape that looks similar to what I showed on the slide before. We have this peak at about 12 eV and then a tail. And then you also see the convolution, because here we also have 2 times and even 3 times scattering, which is why you have these peaks here, which are convolution of the one-time energy loss function. And so we can measure and describe this, and our parameterization is then fitted to this measured spectrum and then put into our model. Systematics are still under investigation, and there's also a publication in preparation. So hopefully you will hear more about this topic soon. Now, I think I'm running a little bit out of time, so I just want to, at the end, go a little bit into our results that we published last year. So the data analysis was on the first 22 days of catching data, where we had a sensitivity to the neutrino mass. And for this, before we could do the analysis, we also had to implement a new unblinding procedure, because we wanted to make sure that we are unbiased for this result. And so we first did our analysis on so-called MC twin data sets, where we generate integral spectra with the same experimental parameters, but with the neutrino mass of 0. And then we can run our fits and test our software on this Monte Carlo data. Then in the next step, run our fits on blinded data sets. And then in the final step, unblind the data and run our fits with the setup that was decided on here. And with this, we can both investigate our systematics on the blinded data sets. For example, we can investigate the endpoint stability over time, but only in the end, we are really sensitive to the neutrino mass. And our systematic uncertainties were treated in 2 ways, by covariance matrix and by MC propagation, and both are in good agreement. So this is one further way of cross-checking our systematics and our analysis procedure. For the unblinding, just a few notes. So KATRIN is not the usual low background counting experiment where we can just blind a certain part of the spectrum and then remove the filter access the whole spectrum because we also need the whole spectrum to investigate our systematics. So what we do instead is we apply blinding to the final states distribution. So I haven't gone into detail about this earlier, unfortunately, but the final states describe the excitations of molecular tritium. And this is one important part that goes into our model. And what we decided on in the end, that we blind a part of this final states distribution by replacing these theoretically computed excitations by unknown Gaussian distribution. And then this unknown Gaussian distribution ensures that we can't extract the neutrino mass from the fit, but it still allows us to, for example, perform endpoint and background fits and so on. So we can perform systematic studies with inaccessible neutrino mass. And then in the end, we use the actual final states distribution for our measurement run, and then we are sensitive to the neutrino mass. And so we did this in the end. And so this is a fit on our first 22 days of data, where we have an integral spectrum over about 90 eV energy range, so -40 below the endpoint, +50 above the endpoint to investigate the background. The data here is displayed with largely increased error bars to make them visible. And again, you can see here that we are mostly dominated by statistical uncertainty. And also on the bottom of the plot, you can see the measurement time distribution that I explained earlier, and where you see that we spend most of the measurement time in a region where we are most sensitive to the neutrino mass at these experimental settings. And we have 27 voltage set points for the retarding energy in this run, or in the setting, and 274 runs in total. And as I mentioned, this is 22 days of data in total, or 22 days of measurement time. And then we come to the new upper limit on the neutrino mass, which is the main result of this first neutrino mass run. We obtain the best fit value using Monte Carlo propagation. And the best fit result for the squared neutrino mass is -1 eV squared with an error of +0.9 and -1.1. So this result is compatible with 0. And we also fit the endpoint, and you can see here, as expected, the neutrino mass and endpoint is correlated, which is normal behavior using the net-E filter. But this is very much how it is expected. And we can also cross-check the endpoint we get from our measurement with the Q value from tritium, which can be measured by other experiments. So the energy difference here is just because the Q value and the endpoint is defined a little bit different. But we can transform the endpoint into a Q value, and then if you compare that with the Q value that was measured independently, we also see a very good agreement. And so we can fit these two parameters and also extract the squared neutrino mass as a main observable. Now to get to the upper limit, we do a sensitivity estimate, and again, we are fully dominated by statistical uncertainty. And we follow two approaches. One is the classic Feldman-Cousins, where we get an upper limit of the neutrino mass of 0.8 eV with our result. And then alternatively, we have the Lokov-Tarkov approach, which was also used for the TRItium experiment, predecessor experiment of KATRIN. And in this case, the sensitivity of our experiment is essentially also the upper limit, as long as we measure negative neutrino mass squared values. And we decided to follow this approach because it removes some of this behavior where we measure negative neutrino masses. And then if you look at the Feldman-Cousins approach, a more negative mass value would improve the upper limit, which is not ideal. And so instead, we follow the Lokov-Tarkov approach, where we have an upper limit of 1.1 eV from our first result of the NU squared. And now I'm coming to an end. So just the last thing, stereoneutrinos, I mentioned them early in the seminar talk. We are also sensitive to stereoneutrinos to some extent because our kinematic method opens the window to perform investigations of stereoneutrinos as well, and even KeV stereoneutrinos we can investigate because our tritium endpoint at 18.6 keV covers a large energy range that includes a few keV below the endpoint as well. And for stereo neutrino, just similar to the normal neutrino, we have a spectral distortion that we can resolve in our integral spectrum measurement. And for EV scale stereo neutrinos, there's also a publication in progress. And for EV scale stereo neutrinos, we can improve the current exclusion limits by the Mainz and Troit's experiment. We can also probe the region of the reactor anomaly, and we can also investigate the hints of the neutrino 4 experiment, which is related to this. And so this is a publication that is in the making, and we have some sensitivity to the EV scale stereo neutrinos. In addition to that, we also have sensitivity to KEV stereo neutrinos. The problem here is that the rate at the KEV scale is too high for the normal KATRIN setup, because we are usually measuring at a few counts per second. At the endpoints, if you go down a few kilovolts below the endpoint, or KEV below the endpoint, the rate is too high. So our sensitivity to KEV steroids is limited for that reason. But in the future upgrade, after KATRIN, we will replace our detector by a twist-turn detector, and the twist-turn detector is optimized for this kind of measurement. So we will do more investigations, especially of the KEV scale steroid spectrum in the future upgrade of the KATRIN experiment. And now, just to put the KATRIN result into context, so KATRIN's first science run was 22 days, but because we had a lower source activity, these 22 days correspond to only 9 days at full activity. And already you can see that the error bars, if you put it into context with our predecessor experiments, Mainz and Troit's, which have published the results around 2000, so now almost 2 decades later, that's the next update, and you can already see that the error bars are much smaller, and in future data taking periods, we will improve on this result much more. So stay tuned. We are now currently doing the fourth neutrino-mass run, as I mentioned earlier, and from now on, we will also do successive data taking periods. So there's one more neutrino-mass run planned at the end of the year, and then in the next years, we will continue with the data taking and add more data and also improve our systematics. And now, for the very last slide, one outlook for the measurement phase we are currently doing is the so-called shifted analyzing plane. I explained earlier how important it is that to control our spectrometer background. And one way that we are now testing is the so-called shifted analyzing plane. I explained the McE filter, where the analyzing plane was in the center of the McE filter. But we can also configure our spectrometer to have the analyzing plane a little bit further to the detector. So this is why it's called shifted analyzing plane. And the reason why this makes a difference is that our spectrometer background is volume dependent. And the volume that matters is the volume between the detector and the analyzing plane. So by shifting the analyzing plane to the detector, we can reduce the volume where background is visible or generated and reaches the detector. And this strongly improves our background contribution, and especially has a strong impact on this non-Poisson background, which is also currently a dominating systematic. And so the next data taking run, which has started last week, is now taken in this shifted analyzing plane mode, and we hope that this improves our statistical uncertainty and also our systematics. And with that, I'm coming to the end. And again, I want to thank the organizers, and also I want to thank the participants for the interest in KATRIN. And I won't go over the slide because I'm already over time, and I'm sorry for that. And I hope we still have some time for questions.
That's great. Thank you, Jan. That was a great talk. We started getting some questions, so I will request Penny Slocum to read the question.
Okay, thank you, Jan. That was a great survey of all of the things that are happening on KATRIN, so thank you very much. I was just wondering in particular about the Rydberg systematic background. Is there a way to reduce it from the experiment, or will it just decrease by itself over time? Or can it be simulated and removed from the data, or some combination of those things?
So one thing that we are investigating is because the ionization is by thermal radiation, we try to cool down the spectrometer by some amount. Of course, we are limited because of other components, but if we reduce the temperature by 10 Kelvin, for example, we can see some background reduction. So this is one way of tackling this, because this is one of the inputs to the generation mechanism. Apart from that, there are not many options that can directly reduce this, because the particles are neutral, so we can't apply shielding. And also the lead 210 has a rather long half-life, or it's part of a decay chain. So also cleaning the surface is not a feasible option right now. So what we are doing now is essentially to use the shifted analyzing plane mode, which would reduce this contribution of the spectron. And one other thing that we are also investigating is to analyze the angular distribution of the electrons, because in principle the electrons generated in the spectrometer from decay have a different angular distributions than signal electrons, but this is something that is very much it needs more work, and this is just an idea that we are investigating right now. Yeah, so for now, our current mitigation mechanism is using the shifted analyzing plane and also operating the spectrometer at slightly lower temperature.
Okay, thanks.
Okay, so I don't see other questions, but I have a question. Could you talk a little bit about the advantages of performing a differential versus integral spectrum measurement for mass measurements?
Sorry, I didn't get that last part.
Oh, sorry. My question is, could you talk about the advantages / disadvantages of performing a differential versus integral spectrum measurement to measure neutrino mass?
So Pranava, do you mean like a counting, like
yeah,
versus absolute counts versus count rate, or what do you mean?
Yeah, that's what I mean. So the left plot here is the differential spectrum, and KATRIN does the integral spectrum measurement. Is there an advantage of doing one over the other for measuring neutrino mass?
I think in principle, it would be better to measure the differential spectrum, because to get to the integrated spectrum, we also need to take care of the response function, and there's more things that go into the fit model to arrive at the integrated spectrum. So I would think that the differential spectrum is a more direct way. And but of course, how our experiment is set up, we can only do the integrated spectrum measurement, because we have to measure the electron energy somehow. But actually, this is a really good question also for KATRIN, because what you're also investigating is measuring the differential spectrum directly, which is in principle possible by using the McE filter in time of flight mode. And from that, you don't integrate the rate, you measure the time of flight, which corresponds directly to the energy of the electrons. And in principle, the McE filter can be used to that. The main challenge is that you don't know the start time of the electrons if you have a radioactive source. So it's very challenging to both measure electrons entering the spectrometer without disturbing the energy. So this is something that we are investigating, and maybe a good solution is available at some point, but for now we will continue with integrated spectrum. But for future, it's definitely one thing to consider.